Today's secret is about challenging distillations. We would like to explain azeotropes, we would like to explain solvent mixtures, and we would like to perform an experiment on the rotovapor. This is the substance we begin with. It's ethanol, technical ethanol. We would like to measure the density and therefore the percentage of ethanol in it. So I use this density meter and we can see it's 93.5% of alcohol. Now let me start the distillation with the ethanol which I filled in here, and now it will take a while. Now let's end this process in the middle in order to find out what the percentage of alcohol is in this side and what percentage is on this side. After the distillation, we have the solvent in the receiving flask and some solvent in the evaporating flask. We've tried to split it up in half, so now I would like to measure the density and therefore the alcoholic content. Let's first start with the receiving flask. First I have to wash it quickly, 2 times, and then let's measure the content. We can see it's 94.0%. Now let's measure the origin substance. And now the measurement. And you can see it's 93.4. So as you can see, there is no significant difference. Now we would like to do a second experiment. This time we have added water to the ethanol. Let's first measure the concentration. This is the cleaning step. Let's do it twice. And the third time counts. And this time we see it's around 37.7%. Let's stop the distillation again at this point, and let's measure the receiving and the evaporation flask. Let's measure first the evaporating flask. We wash it again quickly. (33.5). Now let's measure the receiving flask. And here we end up at 78.8%. So now you can see the big difference between the two. So the separation was partly possible. Let's have a look at this first chart. It's about the non-azeotropic mixtures. We have 2 axes. On the y-axis, we see the composition of the distillate. So that means how much percent purity we have. And on the x-axis, we see the composition of the sample. Again, the percentage. Now, if we look at 40% mixtures, for example, and we draw a line, then we can see that with 40%, depending on the substance and the vapor pressure of the substance, we can see that we can achieve 70% purity by distillation. Another example is if you have 90% purity in your sample and you distill it, you might only, because of the curve, which is getting tighter on the top, you only reach 93% purity at the end of the distillation. Let's have a more in-depth look at the bent curve over here. This curve depends on both solvents and on the vapor pressure of both solvents equally. The next chart has the same x and y axis. Now, this time we talk about azeotropic mixtures, and the curve is very different. You can see it's like a Swan curve, but curved to both sides. And if we have the example we measured before, we could see that the azeotropic point by literature is at 96%. Now we measured 93% and we roughly got 93% back. Now, when we added water, we were at 38%, we distilled, and we got around 80% back. So that is showing that this curve is actually pretty much correct. This last chart shows how the separation is influenced by the vacuum. Now, if we have a look at the line and we draw different lines at different vacuums, we can see the more vacuum we apply, the better the separation gets. In best case, the azeotropic point actually moves up or even disappears. So that means more vacuum means better separation. In addition, the more vacuum we apply, the more this line goes apart from the one before. That means, again, more vacuum, better separation. It's important to mention that some other effects play an important role too. So we can't just have a low vacuum. Things like reboiling, cooling, and the sample, of course, they play a big impact on the choice of the vacuum. So now you understand that separations are not always easy. There are even some physical limits. If you need to know more, please contact your specialist.